Greetings and welcome to the Introduction to Astronomy. In this episode of New Discoveries in Astronomy, we will talk about how astronomers are developing a way to measure millions of exploding stars, helping improve our understanding of the expanding universe and the mystery of dark energy. So let's get started. How can astronomers measure the expansion of the universe when they cannot study every exploding star in detail? One of astronomy's most powerful tools is the Type 1a supernova. Because these stellar explosions reach nearly the same intrinsic brightness, astronomers can use them to measure enormous cosmic distances. But a new generation of telescopes will soon discover millions of these explosions. Studying each one individually will simply not be possible. Astronomers now need a new way to measure the universe on a much larger scale. Type 1a supernovae are often called standard candles because their true brightness is well understood. By comparing the true brightness with how bright the explosion appears from Earth, astronomers can determine its distance. These measurements led to one of the greatest discoveries in modern astronomy, that the expansion of the universe is accelerating. But there is an important complication. Not every Type 1a supernova behaves exactly the same. The galaxy where the explosion occurs, the amount of dust along the line of sight, and the age of the surrounding stars can all slightly affect the observed brightness. Small differences in brightness can lead to small differences in distance. And when measuring the entire universe, these small differences matter. Rather than correcting each effect separately, researchers developed a new framework called SIGARS. The system combines the information about the supernova, its host galaxy, interstellar dust, stellar populations, and even the expansion of the universe into a single physical model. To make this practical, the researchers used artificial intelligence together with large numbers of simulated universe. The AI learns how different physical conditions produce different observations. It can then compare real observations with those simulations to determine the most likely distances and physical properties. Instead of analyzing each ingredient independently, the model interprets the entire system at once. This new approach was designed with the Vera C. Rubin Observatory in mind. During its upcoming 10-year survey, Rubin is expected to discover millions of supernovae. Only a very small fraction of those objects can realistically receive detailed spectroscopic observations. Most will be observed only through the images taken in different filters. The new framework is designed to extract nearly spectroscopic quality distance measurements using imaging data alone. That allows astronomers to learn from nearly every supernova instead of only a carefully selected few. More accurate distances lead to more accurate measurements of how the universe expands. Those measurements help astronomers test models of dark energy, the mysterious phenomenon believed to drive the accelerating expansion of the universe. The framework may also provide new clues about how Type 1a supernovae themselves form and evolve. In other words, improving one measurement strengthens many different areas of astronomy at the same time. This discovery reminds us that astronomy advances through increasingly precise measurements. Every improvement in how we measure the distance allows scientists to build a more accurate picture of the universe. By combining physics, simulations, and artificial intelligence, astronomers are preparing to interpret the enormous flood of observations that the next generation of telescopes will provide. And with each better measurement, we come one step closer to understanding how the universe has evolved over cosmic time. So that concludes our discussion on measuring the universe with millions of supernovae. We'll be back again next week for another new discovery in astronomy. So until then, have a great day, everyone, and I will see you in class.